Welcome to the Explainer. So, you have a new idea. How do you actually prove it works? It doesn't matter if it's a new drug or a new marketing campaign, there's a really simple but powerful tool designed to give you a real answer. It's called the Completely Randomized Design, or CRD. And today, we're going to break down exactly how it works.
I want you to imagine for a second that you've just developed a new medicine. You think it works, you feel it in your gut, but how can you be sure? How do you prove that its effect isn't just a coincidence, just a fluke of random chance? Answering this question is the absolute bedrock of scientific proof and really any smart decision-making.
So here's our game plan. First, we'll start with that basic question. Then we'll introduce the CRD, see how it works in the real world, learn how to read the results without getting a math headache, and finally, figure out if it's the right tool for you.
At its heart, the problem is always the same. Whether we're testing a new drug on patients with a fever, or a new ad on consumers, or even a new teaching method on students, the goal is to isolate the impact of our one new idea from all the other random noise in the world.
Okay, to make this really concrete, let's stick with a simple medical example. We've got 30 patients, they all have a fever. We also have our new medicine, but we want to test 3 different dosages, 1 tablet, 2 tablets, or 3 tablets. So how do we assign these doses to find out which one, if any, is the most effective?
Well, the most direct, most straightforward answer to that question is the completely randomized design. And as the name implies, it uses the power of pure randomness to create a fair and unbiased test.
Okay, so let's break down this definition, because there are 2 absolutely crucial ingredients here. First, the treatments, that's our different medicine dosages, are assigned completely at random. And second, the whole design hinges on a huge assumption that all of our patients are, for the sake of this experiment, basically interchangeable. Statisticians have a word for this. They call it homogeneous.
This idea of homogeneity is really the soul of the CRD. It means we have to pretend that all 30 of our patients are identical. We intentionally ignore their age, their gender, their medical history, everything. But why would we do that? Well, we do it so that any difference we see in their recovery can't be blamed on those other factors. Any other variation we see is just chalked up to random background noise, which we call experimental error.
So, theory is great, but how do we actually put this into practice? The process is surprisingly simple, and it really just boils down to 3 key steps.
Just 3 steps. First, you gather all your experimental units, in our case, all 30 patients. Second, and this is important, you decide before you start how many patients will test each dose. These are your replications. Maybe it's 10 patients for each of the 3 doses. Then, step 3, you assign them randomly. You could literally write their names on slips of paper and pull them out of a hat.
And right here is one of CRD's greatest strengths. It's incredibly flexible. The number of replications, that is the number of patients in each dose group, doesn't even have to be equal. For example, let's say you had 20 test subjects and 4 different treatments. You could randomly assign just 3 people to the first group, 5 to the second, and 6 to the other 2. This is super useful in the real world, especially if some treatments are, say, way more expensive or difficult to administer than others.
Okay, so we've run our experiment, we've collected the data. Let's say we measured how long it took for each patient's fever to break. Now, how do we make sense of it all? Now, the goal here isn't to get lost in the math, but to really understand the core idea. The fundamental question we're trying to answer is this. Are the differences we measured really because of the medicine, or could they have just happened by a random fluke? To figure this out, we use a statistical test called an ANOVA, which stands for Analysis of Variance. And its whole job is to separate the meaningful patterns, the signal, from the random noise.
Think of it like this. All the variation in our results comes from 2 main sources. On one side, you have the signal. This is the variation that's actually caused by our different treatments. This is what we're hoping to find. And on the other side, you have the noise. This is just the random natural variation between our patients that we decided to lump into that experimental error bucket.
The ANOVA test basically just creates a ratio. It compares the variation we see between our different treatment groups to the random variation within each of those groups. So if our medicine is actually working, the differences between the 1 tablet, 2 tablet, and 3 tablet groups should be pretty big, right? If the medicine does nothing, then the differences between the groups will look just like the random noise within them. When that signal is significantly larger than the noise, when that ratio is greater than 1, we can be confident our treatment caused a real effect.
So, CRD seems simple, powerful, pretty great, right? But is it always the best choice? Well, like any tool, it has some very specific strengths and weaknesses you really need to understand.
Let's look at the bottom line. On the plus side, it is the simplest design to set up and analyze, and it's super flexible. But the weaknesses are pretty significant. That big assumption that all your test subjects are the same is rarely true in the real world. And because every other possible source of variation gets dumped into that one big experimental error bucket, the noise can sometimes get so loud that it completely drowns out a real signal from your treatment.
So what's the takeaway here? CRD is at its absolute best in highly controlled environments, like a laboratory, where you can make sure your experimental units, whether they're petri dishes or chunks of metal, are truly identical. It's also great for smaller experiments where its simplicity is a huge advantage.
In the end, the completely randomized design is built on a powerful, simplifying assumption that everything is the same. But what happens when we know it isn't? What do you do when you just can't ignore the fact that some of your patients are old and some are young? Well, that leads us into more advanced designs that are built to control for that variation. But that is a topic for another explainer.